Section 9.1 is on quadratic graphs and their properties. So the main question that we're going to be asked today is, how do I graph a, and I'm going to call it a simple quadratic equation. And first of all, actually quadratic function is a better way to put it, but we'll leave it with that word here. We need to kind of bracket this off and remind ourselves what a quadratic looks like. Quadratic polynomial is of the second degree, and it looks like ax squared plus bx plus c, where a, b, and c are numbers. And I call this one graphing simple quadratic equations because what we're going to do in this first section here, 9.1, is we're going to have b equaling 0. And what that does is it makes them a little simpler to graph and a little simpler to work with. So first of all, before we even start, we have to understand what the general shape of a quadratic function looks like. And if we go back to linear algebra, you've already graphed equations of the form y equals mx plus b. Or, for a specific example, maybe y equals 2x plus 5. And in linear algebra, this was called a linear equation because it's to the first degree. And this told us the slope of the line. If it was positive, it went uphill. If it was negative, it went downhill. And this gave us what we called the y-intercept. So notice these numbers had a very big impact on the nature of the line once it was graphed. Similarly, the numbers that we put in our quadratic equation, or function, ax squared plus bx plus c, are going to greatly affect the graph. But first of all, what we're going to do is, we're just going to look at the graph of f of x, or y, same thing, equals x squared. So you'll notice we don't have a b term, we don't have a c term there, and a is just 1 in this case. And we're going to get an idea of what that looks like. We call this the parent function, and it's kind of what we're going to compare all the other ones to. We're going to be asking ourselves, well, what happens when we take this graph of y equals x squared and maybe we add 2 to it, or put a 3 out front of the x squared? But before we get there, we're going to go graph the parent function y equals x squared. It is the simplest quadratic that we can graph. And to graph it, we're just going to plot some points. And the first point we're going to put in is 0. When I square 0, I get a 0 out. Then I'm going to put a 1 in. When I square 1, I get a 1 out. Likewise, when I put a 2 in, when I square 2, I get a 4 out. Then I'm going to go to the negative side. I'm going to put a negative 1 in. When I square negative 1 times negative 1 is positive. Put a negative 2 in. When I square that, I get a positive 4. And maybe go even to 3 here. 3 squared is 9. It'll give us a really good idea what this graph is going to look like. So 0, 0, 1, 1, 2, 4, and 3, 9, which is quite a ways up there, so I'm not going to graph it, are on the function. And negative 1, 1 is on there. Negative 2, 4 is on there. And when I connect these, you'll note the symmetry of it, and you'll note that it curves, unlike a line. And you should understand, whoopsie, I went over to 3, 4 instead of 2, 4. Let's put that on there a little bit nicer here. There we go. And you'll notice that when I graph it, I get this symmetrical shape, and that's because of this squaring. When I square negatives, I get a positive. When I square positives, I get a positive. So what I've got here is what we call a parabola, spelled P-A-R-A-B-O-L-A. The shape of that graph is called a parabola. This point right here, the turning point, we call the vertex, so we'll label that. This line right here that splits it into 2 equal pieces is what we call the axis of symmetry, because it's symmetrical about that. And then we've just got our, what we call a parabola. So let's move on to the next page. And our first task is just going to be, can you tell me what the vertex is, what that turning point is? And then we're going to talk about two other things that we deal with the graph, which is called their domain and range. But first of all, let's just go up here, and it says, what are the coordinates of the vertex? The vertex is right here where it starts to turn. They're coordinates, which means x comma y, it's a location. This vertex right here's coordinates are at 0, 2. This one right here is at 1 to the right, 1 down. That one's vertex is at 1, negative 1. That's what we call the coordinates of the vertex. Then it asks us whether this represents a minimum or a maximum. Well, you can see on this one right here that this vertex is the highest it ever gets, so we call that a maximum. On this graph over here, this is a bottoming out point. It's the lowest it ever gets, so we call that vertex a minimum. When we're asked for the domain and the range of a graph, of any function actually, the domain is really the answer to the question, what can x be? Really, what can go into the function? Well, I told you that quadratic functions look like ax squared plus bx plus c. And there's really no limitations on that. I can put any number in and square it, any numbers can be added. Sometimes in math, though, there's things we can't do, and that causes us to have to restrict our domain. For example, if I were graphing the square root function, I can't square root negatives, so I couldn't put negatives into my domain. But for a parabola, any number can go in. So a lot of times we'll say all real numbers, or all numbers, or any numbers. When we get into higher levels of math, we say from negative infinity to infinity. But for us, the domain is all real numbers. And for a note right here, the domain for parabolas, or for quadratic functions, is always, so you can't get it wrong, it's always all numbers. And again, the reason for that is because I can put anything, any numbers, I can square, I can add. There's no restrictions on it. And you can see from the graph, I could have put a 3 in, and I'd be way down here or way down here. This graph, these arrows indicate it goes forever to the left and forever to the right, and would continue this way and cover the entire number line along the x-axis. Well, likewise over here then, all real numbers are all numbers. That's always your answer for what is the domain. When we're asked about the range, that's what comes out of the function, or what is y, what can y be, or what's the output. That actually is restricted here because we talked about the fact that for parabolas we have what's called maxes and minimums. The best way to get the range for these is to draw kind of like a fake fence here through the vertex and decide if the parabola lives above or below the vertex, and that'll help us restrict our range on this one. So you'll notice up here that this peaks out at 2, and the entire parabola lives under that line. So we'd say our range is y is always going to be less than or equal to 2. On this one, though, it's a minimum point, and so it's living above that line. That line is down at -1, so we'd say the y's are greater than or equal to -1. So for the range, it's controlled by the vertex. Wherever that vertex is, you draw a horizontal line and consider it a fence, and you're never going to get past that fence. So how do we graph them? Well, we make a table of values, and the most important point, obviously, is that turning point, or that vertex, and we need to find it. Well, what we're going to be graphing right now are some simple ones where we're just going to be having y equals ax squared, or ax squared plus c. We're not going to have a b term in there. So for today, our vertex, when there's no b term, and by b term I mean that middle one, that one that's in front of x, when that's missing, our vertex is at 0, comma something. And we're going to add a little bit to that sentence in just a minute. So here's my x values going in, and my y's are equal to twice my x values squared. So the first thing I want to do is find my vertex, and I like to put that in the middle of my table. My vertex actually, well, here, let's just go put it right here. My vertex, when I put it in, is 0. I go 2 times 0 squared, which is 0. So my vertex is at 0, 0. That's my turning point. Now, once I put in that one, I'm going to put in 2 more. For a line, all you need is 2 points to get an idea what the line looks like. But for a parabola, we have to be a little bit more careful. We need the vertex, and we can't just have one other point because we won't know if it goes like that or whether it goes like this. You need 3 of them to lock it in. One must be the vertex. And then you can put, remember, our domain is all real numbers. We can put anything into that function we want. We're going to be nice to ourselves. We're going to put our nice, easy numbers, a 1 in. Don't forget your order of operations. We do the 1 squared first, and 2 times, we don't do 2 times 1 to the second. We do 1 to the second times 2. So when I put in a 1, a 2 comes out, and then my next favorite number would be a 2, and I do 2 times 2 squared. Again, order of operations, I square the 2 first, 2 times 4 is 8. Once I've got my vertex and 2 others, I'm going to use symmetry to help me graph it, because if this right here is my vertex, then my line of symmetry always goes right through the vertex. So if I'm 1 to the right to get to this point right here, if I go 1 to the left, I will have another point using symmetry. Same here, if I'm 2 to the right to get to that point, I'm going to go 2 to the left. And what that does is it gives me a really nice idea what that parabola looks like. So the process is we find the vertex. How do we do that? We plug a 0 in today. Then we find 2 points, and I like to find them to the right because I like to keep things positive. And then we use some symmetry. Again, our domain is always all real numbers. Anything can go into that function, but not everything can come out. So our range, again, we think this is what's going in, this is what's coming out. You'll notice that I've got this fence right here where the vertex reaches a minimum value. So what I know is that my y's are always living above that line, and for above we think greater than or equal to. The y value there is 0, so that would be my range. Moving on, let's do another one. All right, so first of all, we're going to make a table of values. In our table of values, we would like to have the vertex, which I told you is at 0 today because of the lack of that b term. So we're going to put in 0, 1/2 of 0 squared is 0. Now, we said our domain is all real numbers. So we can put anything in to this function, but whatever we put in, we have to graph. So let's be nice to ourselves. Whatever we put in, we're eventually going to have to take a half of, and I don't like to graph fractions. So I'm going to pick 2, so that when I do 2 squared, which is 4, and take half of it, I get a 2, and it's nice. I'm not having to graph fractions. Likewise, I'm not going to pick 3. I'd do 3 squared is 9, I'd have to take half of it, I'd have to graph a fraction. So I said I'm not going to pick 3. I'm going to put 4 in, and I'm going to do 1/2 of 4 squared, which would be a half of 16. Again, don't forget your order of operations, which is 8. I'm going to go graph those, and again, I chose nice positive values for my x. I could pick anything I wanted, but I chose to make my life easier because whatever I pick, I've got a graph. And again, now we're going to use that symmetry here. If I go 2 to the right, I'm going to go 2 to the left. Here I'm 4 to the right, I'm going to go 4 to the left, and I'll get this parabola right here. And we talked about the domain is all real numbers, and the range of my function again is never drops below this red line. Consider that red line kind of like a horizontal fence. So my range, the y values, what comes out of that function is always living above the fence. The vertex hits it right here at 0, 0. So my y's are always greater than or equal to 0, which should make sense from the equation because we can't square things and get a negative. So that makes sense for that one. I'm going to stop this and I'm going to finish it in a part 2 video.